start recording. Okay, so last topic today. I think there was one quick thing that was brought up to my attention about the REGZ submission. Maybe it wasn't quite clear, but maybe I'll just mention here. For the first one, where it says how many different ways they're placing the cards in order, assume the same number of cards from the first part, right? So 8 hand cards, just to clarify that. I think some people got a bit confused with that. And choosing is synonymous with combinations, right? So that might have clarified this a little bit. And of course, this was meant to be B is equal to this set, which you probably would have guessed. But yes, that's meant to be B there. All right. Anyone have any other issues just with clarity, just with what's required there? Otherwise, I think it's pretty direct, that submission. Repeat one again. I think because it was a bit vague when I say how many different ways. It's the same number. We're choosing the same number of cards as previously. So this one asks for how many hands. This is also asking for how many hands, but if you place the cards in order. So hopefully that clarifies that a little bit, just in case. I think a couple of people mentioned they were that was a little bit vague. Is that clear? Okay, hopefully that's clear enough. Okay, on to today's lecture. So now there's a bit of content here. I want to focus just a little bit more just on more the practical application and examples. So even if you get a bit lost on the theory, at least keep that focus in mind. So random variables and probability distributions. Well, we need a slide for random variables and a slide for probability distributions. So what do we mean by a random variable? It's effectively really just a function. So it's something which gives us outcomes or an event of outcomes based on some number. So a typical thing you might say is if you toss 2 coins, well, there's a random variable of how many heads prop up. So that's a random variable, something that a value that varies. It can be either discrete or continuous, and well, an even simpler example is if we just consider one toss of a coin, heads or tails, then we can just define a random variable being 1 if S is heads and 0 if S is tails. So it sort of indicates whether we have a heads or not. It's useful to assign this as a value, right? And different random variables can be defined on different sample spaces. So for rolling a dice, our sample spaces typical would be getting a 1, a 2, a 3, a 4, a 5, or a 6. Well, we could just say our random variable is exactly that dice value. So we would think that in the event of obtaining a 2, we would output a 2. So this X represents the dice value of a random face. Or we could even define something on Y, which would be 1 if it's called Y if 1 if S is even, or 0 if S is odd. So it would indicate whether the dice face was even or odd. Is it pretty clear, straightforward? Okay, so that's the first part. And how does it relate? Well, given a random variable, a probability distribution is a function which assigns a probability to that random variable. So we're used to talking about probability of events. Here we'll talk about probabilities of a random variable holding a particular value. So with that coin costing example previously, well, I could look at all the distributions of whether my function, my random variable X, outputted a 1, a 0, or something else. So if we go back to that, if X gives us 1 if we toss a heads, what's the probability that we read 1? What do we think? What's the probability that that x value is going to be 1? Thoughts from chat? 1 over 2, yeah. So we have half probability of getting head, so it's half probability of reading a 1. Same for tails, right? And we won't get any other options. So any other value would have no probability. So that's exactly what we'd write here, is that the probability P of our random variable being assigned this given variable x, so think of this little x as being fixed, it's half in the case that this fixed x is 1, half in the case that this fixed x is 0, and 0 otherwise. And we can go back the other way. You could take any arbitrary function and define that as a probability distribution. Typically, you'll often see piecewise functions when you define these things. Do you always have to include the 0 otherwise? Yeah, I guess it depends on the context. So typically you could say, well, we restrict our domain of P to 0, 1 if you like. But effectively, in case we, in general, wish to talk about any real x, then it's best to be on the safe side to say 0 otherwise. So yeah, I agree. If we restrict our domain to be 0, 1, you could ignore this case, but just for BOSUM, I'll include that. Right. Is that not implicit because P can't be more than 1? Yes, well, I guess it sort of indicates whether it's well-formed if we've defined it in a well-formed way. So, yeah, it's a little bit context-driven whether we should include that or not. Maybe I'd say on the safe side you should include it, 0 otherwise. Sometimes you might want to do things like consider when x is 2 for some various reasons, theoretical reasons. And so it's useful to say that this is explicitly 0 rather than just ignoring it. So, but that's just a bit of a technicality, so I wouldn't worry too much about it. Cool. Let me go back to here. Yes, so going back to whenever you can define a function as a probability distribution, well, one of your conditions you just mentioned is right. So it should sum to 1, and we should have a non-negative. We should always have non-negative values. And I mean, of course, we can define any arbitrary type of function, but there are some that are more adhesive to applications and scenarios in the real world. Okay, let's discuss some of them. And again, I wouldn't worry about learning all these, like what these functions look like. The key idea, in my opinion, would be that you understand there's some relevance of these ones. It's really the normal distribution that would be worth exploring, the how to calculate type problem. Okay, so the simplest one that we usually look at is uniform distribution. So that's where we have random variables where the outcomes are all likely. What's a good example of that, do we think? One where the outcomes are all equally likely. Roll of dice, yeah, a fair-sided dice. So exactly. So that's exactly the example, I think. So if we consider the sample space 1, 2, 3, 4, 5, 6, then we can just say, well, our random variable is just the face value, and then we would just say that the probability distribution of obtaining that face value is exactly 1 on 6 for each of the faces. And as you just said, well, a fair coin. Something that's a little bit more interesting is the Bernoulli distribution. And this describes something which could have a pass or a fail, or a success or a failure rate. And we just assign a probability if we pass and give it a complement probability if we fail. So it's really just whether something happens or doesn't happen. So it's really just 2 outcomes that we're interested in. And it's given by this expression. So you can see that we can define this for any P. I'm not sure if I stated this. yeah, this is assuming that p is between 0 and 1 for this to make sense. So we can assign that if we have probability of passing p, then of course, if we can only ever have another event, then the probability that we fail is 1 minus p, and so 0 otherwise. So again, this is useful for saying if something could happen or might not happen. And it's not equally likely. So something like a loaded dice, a weighted coin would be a good example, where it's heavier on one side than the other. Heavy distribution. Where does this come into play usually? Well, there's what we would call the binomial distribution. So basically, it's the distribution that describes n of those passing trials of Bernoulli trials, each with probability success p. So it's given by this mess of an expression. And the idea really is that we need to pass exactly k of the times and fail n minus k of the times. And there's ordering involved, which counts the n choose k. But again, I wouldn't panic too much about how you can see why that's the formula. And it's defined as long as, so we can have any of 0 up to n trials passing, but nothing besides the value of k. And this is just notation for nck. If you haven't seen that, it sort of looks like a vector. And yeah, I mean, at least it does justify that all that stuff with sums, for instance, has some relevance, right? In the real world and in some applications. This goes a little bit beyond what we need to really discuss, but sometimes what we'll do is with this sort of thing, we would approximate it with a continuous probability distribution. I think the last example, it has an example, the last challenge example talks about that. Yeah. So same with discrete, we can look at continuous probability distributions. And the issue is here, before we could look at sums of probabilities at some point. So in this case, we can't say the probability of x equals k, because if it's continuous, then that has probability 0. It's like saying with heights of people, no one has exactly 2 meters height. You'd always be 1 or 2 atoms above that at least. So if we're not measuring up to atoms, we're assuming it's continuously. So based on that, how do we calculate probability bounds? So we'd look at the probability that some continuous random variable is between a and b by looking at, instead of the sum, some integral of some function. And so we call that function the probability density function. So basically, we want to describe the probabilities of being between 2 values as being this integral of this function that we cook up. And so, of course, this would have, if you look at the probability of anything occurring, this should have integral 1 over the whole real line, real values. So some useful examples are the continuous version of the, why we're not going through now, yep, there we go, the continuous version of the uniform distribution. And it's the same sort of idea. Before we had to divide by the total number of scores, which was 6, as a countable number. Here we just divide by the range. So we assign that anything has this fixed value of fx, so the probability will be the integral of this term between 2 values, basically. So it's a way of getting even an even distribution, a uniform distribution. There's the exponential distribution, which is has some implications. Basically, involves an application of using the exponential function. So something like waiting for something to fail over a given period of time, it drops down. Probably the most important one is Gaussian distribution, which is known as the famous bell curve, also known as normal distribution. This varies based on 2 parameters, the mean and the standard deviation, which describes exactly probabilistically the mean and standard deviation of the scores, if scores follow the normal distribution. It's given by this ugly description of a function. It has an exponential of some squared term of x. Again, you don't need to know what this looks like. The key thing is it's sort of it's used quite often, so we use a lot of approximations and bounds based on this. So the rest of the lecture is really just going to focus on dealing with this distribution, not the function, but just the distribution based on it.
That's that table values we look at.
Yeah. So some of the, if you have your tutorial later, you'll probably see looking at the table of values which give us the integral values, which is let's show it now. It's this table here. Okay, so this gives us the probability of being up to some fixed score. Okay, we'll do that in a second. Is that displaying? Yeah, it should be. Anyone seen that before? Anyone heard of the famous bell curve? Is that brand new to a lot of people? I think I missed a couple of comments. Is that not implicit that because P can't be more than one? Yeah, I guess that was back to the Bernoulli trial. It should really be stated, otherwise it doesn't make a very well-formed probability. So yes, you're right that if I'm assuming it's a probabilistic function distribution, then it has to imply that P is between 0 and 1. Actually, it can be equal to 0 or equal to 1, I suppose, technically, but usually we just take strictly. Okay, let's go back to lecture. Okay. And yes, I've just said this, right? I wouldn't worry about knowing that's what this thing looks like. It's just that you can use it, basically. Right, so one thing we might want to look at and discuss is how these distributions work, or how these terms affect, how these parameters actually affect the probability distribution. And they do so as you would expect, that if you look at mean, well, remember that was a way to describe the location of a set of scores. So if you want to take a look at, say, when sigma is 1, so the standard deviation is 1, and the mean is through 1 here, so that's going to actually go through point 1 here. I don't like that being in red. Let me just switch that back to blue. So if we increase our mean, what do you think that's going to do to our bell curve? If we keep the same standard deviation, what does increasing the mean do to its location?
Move it to the right.
Move it to the right. Do we agree with that? That it's simply going to move to the right? Shift left on the x-axis. I think you're thinking of cases where you replace fx with fx minus c. That's the case where if you plus by c, shift to the left. This is a bit different. It's not really the same as applying the function at the mean. It's a little bit different than that. So it's really just thinking about these as a set of scores. Yeah. I can see where them. So if we increase our set of values, we'd expect that the values themselves get bigger. So this sort of describes a whole lot of points usually. So if we increase the mean, it's going to shift everything to the right. We're going to expect to have higher values. And if we decrease the mean, we'll expect everything to shift to the left. So we'll get smaller values. So for instance, if we have a mean of minus 0.5, well, I suppose this is where I would have the red text there. This is going to go through 0.5 as its average value. So that shifts it back. So that's sort of how this would move. So keep in mind, again, we're looking at probabilities of the area under this thing. Right. If we shift so everyone's happy with the mean? If we shift our attention to the standard deviation, well, remember that describes the spread. So what's increasing the standard deviation going to do? Yeah, it's going to spread the values out larger, right? So actually it flattens the curve, and you'd expect also a less of a frequency in between. And so and so that's for increasing the spread. If we decrease the spread, then it's going to bunch everything up closer together. Yeah, so large sigma for larger spread is spreading out. So this is if we have sigma is 1, mu is 0, a smaller standard deviation shrinks everything in closer together, clusters it, and a larger standard deviation spreads it out.
What did you say about frequency?
See how the blue curve here is higher? So basically the function gets a little bit higher because you still want area of 1 underneath the curve. So the actual scores would occur with more frequency closer together if you have less, if it's spread out less, which is what you would sort of expect. If the data points are closer together, you'd expect them to occur more often, a little bit.
In relation to the overall set.
Yeah, yeah. Or you can think it would make sense if I want to keep a constant area of 1 underneath the curve. If I shrink everything in, I need a higher function for the area to be fixed.
Yeah.
Okay, so that's just what it does. Now, this one with sigma is 1 and mu is 0. This is a very standard one, hence the name. It's a standard normal distribution, and basically we perform all our sort of calculations on the standard normal distribution, at least when we base everything down onto things. So basically, this is the most natural bell curve to consider, and so we reduced any problems about normal distributions down to these terms. And I suppose I should mention that the normal distribution comes out in lots of applications everywhere, which is why it's so useful, even though it's such a strange function to deal with. Yeah, so some properties about fx is it has this as a y-intercept, and that's its equation, and you don't need to see that. But that's the equation for fx if it's standard. Anything useful you could spot about this curve? What would be something you could say about this curve if we think about standard properties about functions? It's an even function, very good. Anything else? Anyone from chat? Think there's anything interesting about the curve? I mean, I guess we know the area has to be 1. This shows distribution of money in society. Just kidding. Well, it shows lots of things. That's why it gets used a lot. Yeah. Is it similar shape to 1 on X? Yes and no. I mean, it has some asymptotes, so there's a similarity there. Yeah, I suppose it's sort of more closely related to exponential decay. So it looks very similar to exponential decay, but so that's what you'd get with either minus x. This is either minus x squared. So it sort of does some slightly different things. But yeah, so you get an asymptote there at least. That's common. Let's see what we've listed. So we know it's an even function, symmetric around the y-axis. Something else to point out as well. Would there be a parametric distribution? Oh yeah, I suppose we can discuss it more with you. Yeah, that's another yeah, slightly different distribution. So another thing to mention is the mean is 0, but this is also the most occurring value. You can see it's the highest point as well, and it's also the middle of the values. So all these 3 things are the same for this distribution. It's all 0, and the total area under the curve is still equal to 1, as we mentioned, and we have asymptotes going in the x and y directions. These are always positive. It gets very, very small quite quickly, but they're still technically positive probabilities. So usually you would call, when it's standard, you usually call these Z scores, whatever these values are. Okay, happy to move on, everybody? Again, a bit packed, but just keep in mind this gets used a lot. Cool. Right. Now, because it's actually such a strange, well, it's sort of a non-elementary function you end up with. Basically, it's very hard to compute the integral directly. So, but we know we have tables, as you just saw, tables of probabilities for the standard normal curve. And so the idea is, in a lot of applications, we have a normal distribution. We convert to Z scores and compare them. Yes, which basically says we want to shift everything back to our mean of 0, so shift it left or right, and then scale the spread, so basically times or divide. So that's the process of standardization. And so the key thing to, yes, the table we've just seen just now. Oops. The key thing to consider is this expression. So if we have x being distributed with mean mu and standard deviation sigma is given, which is normally non-standard, we standardize the scores, so we find the z-scores of each x score, which we usually call of x, by subtracting off the mean and dividing the standard deviation. So that's the process there. Okay, great. So we have some examples coming up. So any thoughts just on the theory up to this point? I think the rest is really just running through some questions. Okay, so let's see it in practice. So we have some data set, and we know how we've calculated that it has a mean of 50 and standard deviation of 15. And it's worth noting that it does say that it's normally distributed. So it follows that bell curve. And want to convert the following scores into z-scores. So 65. What do you think? What do we get as our z-score of 65? Any thoughts? So we hear 1. Or do we agree from chat? 1, yeah. So all we have to do is subtract off 50. So it's 15. It's a value of 15 away from the mean, higher than the mean, and that's one standard deviation lot. So we get a z-score of 1. And it's more useful to say, rather than say it's 15 away from the mean, is to say it's 1 z-score away from the mean, because it gives us a common probability, right? It sort of fixes how close it is. 75, what's the z-score? What do you think for this one? Yeah, I guess it'd be 25 on 15, which is 5/3, as you mentioned, which is 1.12, so 1.67 to 2 decimal places. Typically in the tables, this is measured to 2 decimal places. Finally, 40, do you expect a positive or negative number for our z-score? What do you say? Negative, do we agree from chat? Why do we think it's a negative z-score?
It's lower than the mean.
Lower than the mean, agreed. It's lower than the mean. So we're going to get 40 minus 50 on 15. So that's a z-score of about minus 0.67. And right. So for this next one, well, we're considering another normally distributed data set, mean 60, standard deviation 12. And this time we actually want to work our way backwards. So we're given z-scores, we want to find out our value of x. Well, if we want a value of z equals 3, well, you could say we just need to solve for x, right? So if we have a z-score of 3, then we'd expect 3 to be x minus 60 on 12. So this is going to be 3 standard deviations away from x, which means we're 36 of units or whatever the data is measured in away higher than 60, so x is 96. So you can think of just solving backwards this one. Same for z equals minus 1.25. So hopefully the process is pretty straightforward at this stage. We're solving minus 1.25 is x minus 60 on 12. Multiply the 12 and add by 60. We should end up with 45. Okay, all good so far, everybody? Great. Okay, so z-scores, as I mentioned, sort of fix how far away things are probabilistically. So let's think of this example. If we take 2 class tests and assume that amongst all the students that the scores are normally distributed, and let's say we've computed at least the mean standard deviation of these values. So we know that out of all those people, in test 1 they had mean 60, standard deviation 6.2. In test 2 we had 58 as our mean, 6.0 as our standard deviation. And we know that Stuart scored 63 in test 1 and 62 in test 2. And the question is, he thinks he performed better in test 1. Do you agree? Justify your answers with appropriate calculations. Well, what do we think? So do we think that just because Stuart obtained 63, which is higher than 62, did he do better in test 1? What do we think? He achieved a higher test score. Better in test 2, but why? As a raw score. Yeah, that's the issue, is that just to, I suppose, to specify it a bit closer, if it says perform better, he got a better raw score, but was that better compared to the rest of the class? So that's probably a better indication of how well he performed, right? Maybe. Why? People don't get that, you're not getting that high marks? So what we need to do is consider this as a, in terms of the spread of the test, right? So for instance, in test 2, there was a lower mean anyway. So, I mean, you could just think, well, maybe it was just a harder test. So we should sort of compare amongst the Z scores, because that gives us a better illustration of how well, what's the better probability that someone did better. So that would be constant amongst the scores. So what do we mean by that? So let's compute the 2 Z scores. Well, for the first Z scores, well, okay, that jumped a bit further than I meant to. For test 1, well, we would compute that this is the 63 minus the mean, which ends over the standard deviation, which is 0.4839. So in test 1, Stuart scored amongst at a rate of about almost 0.5 standard deviations. If we look at test 2, we subtract off the mean divided by the standard deviation. Stuart was amongst the 0.67 roughly Z score. So it's a higher Z score. So if we sort of clarify it this way, in test 2, he did better than more. He probably did better than more people, right? He did better than the higher proportion of people versus test 1. So this is a higher Z score. So it's test 2 was done better if you compare to the rest of the students. So that's what I mean by it gives us a common ground to compare. Let's move on. Let's think about what's the probability that Z takes on values between 0 and 1.9. So this is one of those typical ones where we would want to use the table. So the idea is we want to look at this region and we want to find the area of this region. And again, we can't directly compute the integral, so we use our tables, and our tables will tell us, our tables give us all these various areas up to some right bound here. Okay, so for this one, well, it's not quite the lower bound. How far away would this be, say, from the probability that Z is less than 1.9? How could you compute that? So less than 33.5. Well, I guess you're just guessing, right? So if we want to be more accurate, we can sort of sum these in terms of areas up to a right bound, but we have to account for the fact that we're not including everything less than 0. Yes, there will be. If you need to use that for a for an exam question, then you'll be provided the table if we have to compute some Z scores. So basically for this one, if we want to compute this, we'd look at the range of values up to 1.9 and subtract off the range of values up to 0. And let's use the table for less than 0, but you could probably guess what that has to be just from the symmetry. So I'd look at this, and maybe if I zoom in a bit. How do we use this table? Well, we look at the Z score. It's positive, so I want the right table here. And we read this as the whole number, the first digit, and the second digit here. So you might have a bit of practice with this. So if I want the one that's less than 0, it's just this first entry, which is 0.5. It's a half, which you can probably guess just from the fact that it's halfway. It's at the midpoint. Compare that with 1.9. If you want to look up the tables to find where 1.9 lies. Then we run down, it's 1 here, first digit is 0. The second digit is also 0, so I only want the first column, otherwise you might do something larger. So I want this entry. Sometimes I'd probably just line this up to more clearly zoom in where this is or something. So that's going to be 0.9713. So let me zoom in a bit further. It's going to be this entry here. Okay, which sort of seems reasonable, so about 0.9713. So putting that information together, it should be that value minus the 0.5, so we end up with a probability of 0.4713 inside this region here. So that accounts for this, the area under the curve here, the probability that our z-score is between 0 and 1.9. Okay, happy with this one? I might sort of skip a bit ahead to an example, an application. Yeah, okay, I might do this a bit quicker. So, for probably between 0 and 2, we can compute this on the probability that z is at most 2 minus probability z is at most 0. And I won't look up the table so much more anymore. You can practice that a bit yourself, but we should get 0.9772 minus 0.5. 0.4772. What about this probability? What do we expect this one's going to be? Any thoughts? 0.4772. So does it matter that these are strict inequalities? Yes or no? So this really only accounts for the probability at a point, which I mentioned was 0. So it doesn't really matter if these are strict or not. So they don't contribute to the probability, they don't contribute to the area. So it's the same as before. So you don't have to worry about whether you include or not include these for the continuous probabilities. So they both represent this area, whether you include the boundary or not. If you want to do one where there's a lower bound, well, the main idea is we can use complement probability, right? So in this case, we're after this area. Well, I know that it's just going to be 1 less the probability on the left. So it should be 1 minus the complement event, which is the probability that z is less than or equal to 1.25. And then we look at 1.25 in our tables, which will end up being 0.8944. So maybe because it has just to check that makes sense, if we look at 1.25, here's 1.2. To zoom in a little bit more. We just try and match it with 0.5. So it's going to be this entry here, 0.8944. And that gives 0.1056. Sometimes you can use symmetry of these curves to calculate that. Okay, minus 3 to 3. Again, I'll skip through this a little bit because it's almost the same sort of thing as the previous one. But the idea is we want the area between these bounds, so we can simply find the area up to 3, and then subtract off the area up to up to minus 3. That'll give us what's in between here. Yeah. Or alternatively, we could note that it's really just going to be 1 minus what's over both endpoints. So 1 minus 2 lots of the probability that z is less than minus 3, so that's going to represent that area here, which if we look at the table is 0.001, so the whole probability should be 0.9974. So maybe you can double check that using the other approach. I might skip this a little bit because I will put the slides up anyway. For this one, okay, so I guess the problem here, this one, it's a bit different. We want to find the Z values, which is going to give us a probability of 0.95 in between. So an approach with this one is to note that, well, I can rearrange to trying to find the Z value for which this should be some probability. And I know that there's some symmetry involved, so this should be half. This should be precisely half of the sum of both of these, which is going to be 1 minus the actual region in here, which is the 0.95. So just to spell that out a bit, each tail area should, the tail area is summed to 0.05, so each tail should be 0.025. So what we want to do is we want to work out the Z score, well, minus Z0 score. That gets us this probability. And the difference here is we would look up the actual value, so 0.025, which would be about 25 somewhere here, this one. So that tells me that I want the Z score, or something close to, if it's not exactly there, minus 1.96. So that's to work backwards the Z score. Again, you'll practice this a fair bit in the tutorial, I'm sure, a little bit. So this term itself should be minus 1.96, which means the Z0 is actually going to be 1.96, because we were looking for minus Z0 for this example, which makes a bit of sense. So 95% of the points are between 1.96 and minus 1.96. This one's the same sort of idea. So I'll do it quite quickly. The only point to make here is that if we look up 0.005, I believe there isn't a precise value. So I guess in this one we do. So we get something quite similar. But do note that these are only approximate to 2 decimal places for Z0 and 4 decimal places for the probability. Yeah, actually, let me just look back at the table again. Yeah, 005 would be here. So it's not exactly on the table. So it would make sense to either give it minus 2.58 or minus 2.57. So if you're that close, it's usually fine to use either of them. Great questions, comments so far. This one, I think we can probably skip it a little bit. Basically, the idea here is we could use it to find IQR, basically because we can find the Z score, which is going to give us the quarter point and a 3/4 point. So Q1 and Q3. So to find Q1, we could look up the standard table, find that minus 0.67, and for the Q3, we would look up the higher point. So where this is plus, this goes up to 0.75, this ends up being 0.67. There's symmetry involved, right? So the IQR is 1.3 to 4 between those. Okay, so I guess this is the one I was wanting to focus on a bit. So what are we going to do for applications? Well, typically we'd get some application where we have some mean, so non-standard, say 14.31, and a standard deviation of 6.40. So what sort of a question we might ask? Well, given the average is about $14, we want to make it what's the percentage of purchases that were made that were under $10? Well, what we want to do is basically find the probability that our random variable of our purchases should be less than 10 in this, given this mean and this standard deviation. So we want to calculate this value. We don't know how, it's non-standard, so we need to standardize the Z scores, and then we can use our tables. So we standardize the Z scores by, again, subtracting off the mean and dividing through by the standard deviation. So that's our formula. So really, this condition is the same as this condition. The difference here is that this left-hand side is the new standard normal distributed, and the right-hand side is the z-score we want to compute against. So if we simplify these terms, well, left-hand side is z, and simply computing this value will get us minus 0.67. So this boils down the problem to trying to find the probability that z is at most minus 0.67 z-scores, and then we can use our tables. Then we can use our approximation techniques that we know these values, which gives us 0.2514. Okay, and just to spell that out, especially as we're given this as a requested this as a percentage, we would say that approximately 25%, or maybe approximately 25.14% of purchases were under $10. Just to tie that back to the problem. Okay, so just let that sink in for a second. So standardize to z-scores, compute the probability. Let's keep the same example. Let's say we're still at the same retail store, and this time we want to go back the other way. We want to work out what purchase amount would mark where we hit the 20% of the distribution. You know, we want to give a to reward the salesperson that makes more than the, you know, sells things at higher than 10% of the cost or something. The highest 10% of values. So what we want to do is note that, well, if we're trying to find the upper 10%, well, we'll try and work out where the probability should go to 90%. So the probability should be equal to 0.9, and I'll leave you to double check on the table. That should give us a z-score of 1.28, which means that we want to work out the x-score, so the actual retail amount, the purchase amount, that corresponds to the z-score, and then we just solve backwards. So we know our z-score itself from this formula should be 1.28. So we solve backwards to find our x-score. So we multiply by the standard deviation and add by the mean, which is going to give us 22.5. So this is the dollar amount. So $22.50. It's going to give us will give us where we'll mark off the cutoff point of the highest 10%. Any questions so far? There's one more example, and it goes a little bit beyond the course, but maybe I'll just add it in the last 5 minutes on the recording. It's more just of interest. So basically, it relates back to approximating. So I wouldn't panic. This is sort of more outside the course a little bit. So let's just say not examinable. So I can put the magic word in here. There we go. And it just justifies that we do use this technique in some cases. So the idea is, let's say if we have Albert and Boris that play 100 games of checkers, and they want to find out the superior player. And what do we want to do? We want to calculate the probability that one of them has at least 95% chance they didn't win all the games by luck alone. So an approach for this one is to work out if it was just by random luck, find the cutoff point of where the probability is 95%. So if it's purely by luck, the probability of success of an early trial is a half, which gets us this mess of an expression from the binomial distribution. So basically, you want to find the n such that the sum of such terms should be 0.05. So that's going to mark off the cutoff point with this 5%. So again, don't forget this is, you don't have to worry about this detail. I'm just add on what we was talking about. And this is very hard to do theoretically in practice. So what we do instead is we just approximate it. So there's a technique for approximating it with the normal distribution. which means the new mean should be n times p, which is 50, and the new standard deviation should be 5. So you just take that as given for this one. And so we can work backwards to work out that our z-score should be 1.96, and then use the new this given mean and standard deviation to work backwards, which means that our z-score should be about 60, which means to tie everything together, if the player would have to win more than 60 games of 160 of the 100 games, if they win more than that, then there's less than 0.5 chance that they're just randomly guessing. So that would be enough to say that it's more likely they're skilled than not. Okay, so that might have been much, but it's more just sort of a little bit of an aside, right? Just to see where these things can go. I'll put the magic words back on this slide for us all. There we go. At least this last example is not examinable. Cool. All right. So that's the course. So so in terms of assessments, there's just the one submission, which is going to be Friday for most people, and then the final exam on the Wednesday. I might put some images of the location of the place as well. The up to what lecture in topic 5. It'll include things. It'll include things of using the table, so I'll let you know that. So maybe not so much all the theory stuff, but there's a question on using the table. And you'll be provided for it in the exam. Hope there wasn't too much of a hint. Oh well, I'll tell you what to prepare for. All right, any other queries, questions? Who provides the tables? It'll be part of the exam question sheet. You'll just get it printed out. So we'll give it to we'll give you the and we'll also provide the working out paper. So no, you don't have to provide it as part of your cheat sheet. Yeah, we wouldn't expect you to have to worry about copying down those tables. Maybe we should have made that more vague. I should have been more. There could be a question using the tables in the. All right. Otherwise, okay. So I guess that's it, at least in terms of in-person classes and stuff. What are the rules on pencils and pens? I'd really prefer you just bring in black and blue pens. Yeah. Otherwise, it's. Do we have a thing on here? I guess I'm supposed to better pack up. Thanks. Nice. See ya. See ya. Any other questions? I'm just also going to pack everything up as we go. Hey, it's going. Do you want the screens and everything?
Just the screens, aren't you? Great.
Yeah. Oh, okay. Fair enough. Cool. Thanks all. All right. Best of luck with everything. Good luck with the exams. No other queries? End of the course. Let's end the recording here. Okay. Thanks everyone. See ya. All the best.